Let's continue on chapter 5. Today we're going to talk about volumes calculated by cylindrical shells. The idea is very easy to follow. So first, let's look at this cylindrical shell. Let's say we're given this shape that is a cylinder with an empty, the inside is empty. So let me go back to the original picture. I kind of compare it to this because the drawing, it's not that easy to see. So let's assume you have this shape and the height is given as h. The radius, say up to the middle, is given as r, and there is a thickness to it. That thickness, we call it delta r. The thinner that shell is, the more accurate our estimation will become for the volume. So if you have such a shape, the volume is simply the area on top multiplied by the height. And the area on top is the circumference multiplied by the thickness, which is the delta r. The circumference of a circle is 2 pi r. The thickness is delta r. So this product is kind of an approximation of this area on top. And if you multiply it by the height, what you get is the volume of this cylinder shape. So this volume is 2 pi r h delta r. Normally, if you're given a function f, so if you're given a function f and they say given this area under the function, by rotating this around the y-axis, you will create a cylindrical shape. It's not a cylinder, but if you look at this in smaller pieces, each piece will correspond to a cylindrical shape. So if you break it into, let's say, 5 pieces, each piece will be a cylinder, and you approximate a volume of each of these cylinders, and you add up these volumes, that would be an approximation. The more pieces that you add on, the higher the approximation becomes. And that's the same idea that we started for the area and then the volume, and now we're going to discuss the cylindrical volume. So what you need to notice is what is the radius for the approximation. So if you look at any of these cylinders, there would be a radius and some height. So what is the radius and the height? So let's say we focus on one of these cylinders. From the point 0 to here, this is the radius of the circle. It's basically the x coordinate. So the radius is nothing but x. So let's say r is given as x. What is the height? If picking the point x, corresponding y value is the height. The y value comes from the function. So if I have a point here as x, the height is basically the height of the cylinder that's created by this rotation. So the height is f of x. And this delta r is the thickness. So if we let x vary, so it's basically the change in x, which we write it as the dx. So what you notice is each volume would be 2 pi times x times f of x times dx. And if we add up all those volumes, we get an approximation for the total volume. So we can say this theorem that the volume of a solid in the figure obtained by rotation. So let's say this, focus on this figure 1. We rotate the function f and the area underneath it. Around the y-axis, there would be a volume. This volume from A to B. This volume could be calculated by calculating the integral 2 pi x f of x dx. And again, all these approximation, this is a circumference multiplied by the height multiplied by the thickness. So this is basically the idea for the calculating a volume of a cylinder shape by rotating about the y-axis. If it's rotation about the x-axis, we've already discussed it, but you can change the x and y coordinate and calculate that as well. Okay, so let's focus on some examples. I'm going to use this formula. We already discussed rotation about the x-axis in the last section. We did an example of rotation by y-axis by interchanging x and y as well. There was an option. But let's focus on this idea of the cylindrical shape. So let's say given this function y equals to 2x squared minus x cubed, and the area between this function and y equal to 0, we want to rotate this about the y-axis. So I picked this example because there are pictures and it's easier to notice. Okay, so let's say, what is the area underneath the function? The function 2x cubed minus x, 2x squared minus x cubed basically looks like something like this, and it continues going on. Maybe it will go up again, something like that. Whatever it looks like. This area is what we're going to rotate. So I'm going to ignore this part. And if you rotate this about the x-axis, about the y-axis, you'll kind of create this shape. You'll kind of create this shape. Well, my graphing is not good enough. That's why I picked the pictures. So this shape by rotation is basically what you get is this picture. And if you rotate the curve, it's like a torus, but it's not basically a torus because you don't have a hole at in the middle. It's a kind of donut shape, but not circular. So what we need to know is, first you always find a and b, the starting point and the end point of the function. So basically you want to find out the intersection of these two. So where do you have 2x squared minus x cubed equal to 0? You can factor out an x squared. You'll have 2 minus x equal to 0. So what is either x is 0 or 2 minus x is 0, which x equals to 2. Which means the starting point is 0. The stopping point is at 2. That's what we figured out by doing this calculation. Okay, so this end starting point 0 and end point 2. So if we rotate this, what we get is the height and the radius for each cylinder. So the radius r is basically x, the distance from the y-axis is x, and the height is the value of the y value of the function. So the h is f of x, which in this case is 2x squared minus x cubed. So what do we need to do? We calculate this volume. What is the volume? From 0 to 2, 2 pi times x times the height, which is 2x squared minus x cubed, multiplied by the thickness dx. And we integrate. At this point on, everything is simply polynomial. I'm going to write the 2 pi outside since it's constant. From 0 to 2, you'll have distribute this x as well. So you'll get 2x cubed minus x to the 4th dx. Find the antiderivative. The 2 pi is still there. The antiderivative would be 2x to the 4 divided by 4 minus x to the 5 divided by 5. Evaluate from 0 to 2. If you replace 2 into the function, what do you get is 2 pi 2 times 2 to the 4 divided by 4 minus 2 to the 5 divided by 5. And if you replace 0, we get simply 0. And if we add up all those numbers, that is 32 over 5. This one is 32 over 4. 1/4 minus 1/5 is this is 64 pi divided by 20. I think. Yeah. You can simplify it to divide by 4 again. This would be 16 pi over 5. Again, you can double check my work, make sure that it's correct. It's the idea that matters. You should use calculator when you subtract these fractions just to double check your work. You should do it by hand, but use calculator to double check your work always. Okay, so we found the volume. The volume is 16 pi over 5. Okay, let's try another example. Find the volume of a solid obtained by rotating about the y-axis. What are we rotating? The region between these two functions. Okay, so again, you always need to figure out where is the boundaries. So we set the functions equal to each other. X minus x squared equal to 0. X times 1 minus x would be 0. Therefore, x is 0 and 1. Okay, so whatever these two functions look like, here is y equal to x, here is y equal to x squared. This is x squared, this is x. The starting point 0 and ends at 1. This is the intersection points, the x coordinate of the intersection point. So what are we rotating? We're rotating this area about the y-axis. Okay, so what you should notice is now the radius is still x. If I pick x to be here, this radius is still fixed x. But the height is kind of different now, because the height of the cylinder that creates the rotation is now, here's the picture. If you look at the picture, the height is basically created by the two functions, not only the top function. So it is the difference of the top function minus the bottom function. This is the height of the cylinder. So I know radius is still x, but the height would be difference of the two functions. H would be the top function x minus the bottom function x squared. This is important. In the last example, the height was correspond to the function, because this height basically was the height of the cylinder, which is the y value of the function. This example, height corresponds to the cylinder is basically the difference in the two functions, the top function minus the bottom function. And so we can calculate the volume. Try to always figure out what is the radius and what is the height. Then you can replace it in the formula. From 0 to 1, we found the boundaries. 2 pi times the radius, x, times the height, x minus x squared, times the thickness, dx. And at this point on, it's just a simple integral. And always do this. Keep the 2 pi out, evaluate the integral. Distribute the x. We get x squared minus x cubed dx. And this is 2 pi. The antiderivative of x squared is x cubed over 3. The antiderivative of x cubed is x to the 4th over 4. And evaluate from 0 to 1. What we get is, let me write it here. We get 2 pi times, again, good thing is by replacing 0, we get 0. So by just replace 1, you get 1/3 minus 1/4. 1/3 minus 1/4 is 1 over 12. And you'll get pi over 6. There we go. So this is the volume created by this rotation. Okay, so we did an example that the height was the height of the function. Now we do an example that the height is basically the difference between the two functions. Now, what if the radius changes? So here's an example that you notice that the radius is not going to be simply x. Okay, so let's consider the function, the area between these two functions, which are already, okay, there's a picture of it, but let's try again to figure out what is the intersection point. Always set the two functions equal to each other. This function equal to 0. That will give you a better idea of where the intersection points are. X times x minus 1 or 1 minus x equals to 0. So x equal to 0 and x equal to 1. So basically the intersection point, here is the two graph. Y equal to 0 is the x-axis. and the other graph is a parabola upside down. So basically it's from 0 to 1, which is correspond to this curve. Intersection point is 0, and the other intersection point is at 1. Okay, so let me erase this. There's a better picture already here. So this intersection point is at 1. That's what we figured out through this, setting the two functions equal to each other. If they would have said to rotate this about the y-axis, then the radius would have been simply x. But now the question says, rotate this about the line y equal to 2. So let me draw that. We have this function, to 1, and we want to rotate this about the line, vertical line y equal to 2. Sorry, x equal to 2. It's 2. Okay, so if we rotate this along this line, what you get is some cylindrical shape. The height, if I can draw this better. Here we go. Here's the height, and we're rotating this. Along the line y x equal to 2. So the radius is basically this length. So if I say x is here, that would be the radius. This is the radius. So in the picture, you notice that there's a cylindrical shape, and if you locate x to be at this location, the difference here is basically the radius. Well, how do you find the difference? Is the distance between 2 and x is 2 minus x, the difference between those two. And how about the height? The height of this cylinder is basically the same as the y value of the function. That's the height of the cylinder. And the y value of the function is x minus x squared. Again, in all of these examples, polynomials have been used, but you can have trigonometric functions instead of x minus x squared. This could be sine function, sine x. Just because there were pictures, I picked these examples. It's not going to be any different. It's harder for me to draw the 3 dimensions. That's why I picked these. Okay, so how do we calculate the volume? 0 to 1, we found the boundaries. 2 pi times the radius. Radius is 2 minus x. Times the height, x minus x squared, times dx. If you get the idea, you don't need to really memorize the formula. You can always go back to 2 pi r h delta x. This is how you approximate the volume of a cylinder with a thickness delta x, height h, and radius r. Okay, so this is, keep the 2 pi, distribute that 2 minus x. Let's see what we get is 2x minus 2x squared minus x squared plus x cubed and dx. We can simplify it a bit more, so let's do that. From 0 to 1, we have, I'm going to put them in order, 2x cubed minus 3x squared plus 2x dx. And what is this integral? Keep the 2 pi. The antiderivative of x cubed is x to the 4 over 4. The antiderivative of 3x squared would be 3x cubed over 3. These two can cancel out, so I'm going to write just x cubed. And the antiderivative of 2x would be x squared. It would be 2x squared over 2. The 2's again will cancel. And we evaluate from 0 to 1. If you replace 1, you get 2 pi times 1/4 minus 1 plus 1. And if you replace 0, you'll get 0. So basically, these two will cancel out as well. You get pi over 2. And here's the volume. This is the volume created by this rotation about the line x equal to 2. If, here's one thing. Sometimes the line is on the other side. The same question. You had this curve. This is x. if they say rotate this about, let's say, x equal to -2 instead of +2. You're rotating this cylinder, this area, about the line y equal to -2. What you get is now this length becomes the radius. So what would be that radius is this length plus x. So that length would be 2 plus x. Or you can always say the right endpoint minus the left endpoint, which is x minus -2. It's the same as x plus 2. This is the radius. Okay, so be careful to figure out the radius properly, the height properly, the cylinders. And after that, it's just calculation through the integral. Okay, nothing too complicated. So I'm gonna stop here and we will continue this topic next time.